Hello everyone, welcome back to online survey video tutorial on applied hydraulics. So in the previous class, we have seen the draft tube theory. In this class, we are covering a unit quantities. Okay, so let us see what is unit quantities by the way. See, unit quantities are very essential to predict the performance of the turbine. So under various conditions like under varying head condition, varying speed condition, varying output and gate opening conditions. So it is used to check the performance of a turbine. So and those behaviors or the performance are expressed in terms of a quantity. So basically, so unit quantity means so when the performance is checked when the head of the turbine is 1 means unity. When the head on the turbine is reduced to unity, whatever the behavior of the turbine so is going to obtain. So those are expressed in terms of quantities which are called as unit quantities. So the conditions so of the turbine under unit head so are such that efficiency of the turbine remains unaffected. So when you check the conditions of turbine for a unit head condition, so the efficiency will remain unaffected. And also there are three main important unit quantities under unit head. That is unit speed, which is given by nu, which is equal to n by root h. So which is nothing but the speed of the turbine which works under unit head, that is h is equal to 1 meter. So the second one is unit discharge, which is denoted as qu is equal to q by root h. So again, it is same, the discharge passing through the turbine when working under unit head. And the third quantity is unit power, which is given by pu is equal to p divided by so h to the power 3 by 2. So which is the power developed when working under unit head. So these are the three important unit quantities. So let us in detail discuss how we obtain these equations for these three unit quantities. So the first one is unit speed. So for that, let us consider n is the speed of the turbine under head h, and h is the head under the turbine. So u is the tangential velocity and v is the absolute velocity. So we know that tangential velocity is directly proportional to the absolute velocity, and from the absolute velocity equation, v is equal to square root of 2gh. So we know so v is directly proportional to root h. So if you substitute that here, you will get u is directly proportional to root h. And we also know that this tangential velocity u is equal to pi d n by 60. So according to this particular equation, the varying parameter is speed because we are obtaining the equation for unit speed. So u is directly proportional to n, or n is directly proportional to u. So you just substitute this here in this particular equation. So you will get, so n is directly proportional to root h. So and if you remove this proportionality, you will get a constant that is represented as k1. So n is equal to k1 root h. So let us find this k1. So to find k1, so we'll consider the unit quantity definition, that is when h is equal to 1 meter, n will become unit head, that is nu. So if you substitute that, nu is equal to k into root 1. So k you will get as nu. So substitute that back in this equation. So you will get k is equal to nu, n is equal to nu into root h. So where nu is equal to n divided by root h. So this is the equation for unit speed. The second one, you have the unit discharge. So similarly, let us consider h is the head of the water on the turbine, q is the discharge passing through the turbine, and a is the area of flow. And we know the general continuity equation, q is equal to area into velocity, and the area remains constant. So you can write this equation as q is directly proportional to v. Okay, and if you remove this proportionality, you will get q constant, which is called k2. So q is equal to k2 into root h. And let us substitute the, because how we already know v is directly proportional to root h, so we have substituted that also. So according to the definition of unit discharge, when h is equal to 1 meter, q becomes qu. So substitute that here, you will get k2 as qu. So q is equal to qu root h. So where QU is equal to Q divided by root h is the equation for unit discharge. And similarly, the last quantity is a unit power. So for that, let us consider the same parameters, like H is the head of water on the turbine, P is the power developed by turbine, Q is the discharge through the turbine, and let us consider the efficiency, that is overall efficiency is power developed by water power, that is nothing but shaft power to water power. So shaft power is denoted by P. Okay, so eta naught is equal to P by rho G QH divided by 1000. So this is the water power. So we have to get an equation for power. So let us rearrange this. So for a power, if you rearrange, you'll get P is equal to eta naught into rho G QH divided by 1000. So here this eta naught rho G divided by 1000 is a constant. So you can write that equation as power P is directly proportional to Q into H. And we already know this Q is directly proportional to root H in the previous unit discharge equation. So P will be directly proportional to root H into H. So root H into H, you'll get P directly proportional to H to the power 3 by 2. So, and let us apply the definition of unit power. Okay, when P is equal to 1 meter, H will be equal to, sorry, when H is equal to 1 meter, P will be equal to PU. So if you substitute that, then you will get PU is equal to K3 into 1 to the power 3 by 2. So if you remove this constant, like proportionality, you will get a constant that we have taken as K3. So you'll get P is equal to K3 into H to the power 3 by 2. So after that, we have applied a definition. So when H is equal to 1 meter, P will become PU. So if you substitute that K3, you will get it as PU. So substitute this into the back to this equation. So you'll get P is equal to PU, H to the power 3 by 2. So PU is equal to P divided by H power 3 by 2 is the equation for unit power. So these are the three important unit quantities. Thank you all. Let us continue in the next class.